The reason why we have been learning, one of the reasons why we have been learning implicit differentiation is that it's useful to find the formulas for the derivatives of the inverses of the standard functions. So for example, the logarithm has a very simple formula. The derivative of the natural logarithm is 1 over x. And this is a formula we need to know. But how do we get here? Why this formula? So the logarithm is just the inverse of the exponential, right? So when we write this equation, the exponential, here I don't know how to take the derivative of the logarithm, but here I have exponential that I know how to take the derivative of. So let me use implicit differentiation there and take the derivative ddx of both sides. The right-hand side is going to be 1. The left is going to be the exponential of y times dy dx, and then equal to 1, because that was the derivative of the right-hand side. And from there, I get dy dx equals 1 over the exponential of y. And then remember that the exponential of y equals x, okay, because y is the logarithm. So then this is 1 over x. Okay, so that is the way we get this formula, the derivative equal 1 over x. Now, for the ones of you that have allergy to anything that looks like a proof, this computation is very important to know, because sometimes, for example, if you are given f of x equals the logarithm in base 10 of x, so how do you find the derivative f prime of x? So if we don't remember the formula, we are kind of done, right? Unless we remember this trick that I just shown you, we can say, well, okay, because this is the inverse of the exponential with base 10, so I can raise 10 to the power y, and I'm going to get x. This is by definition of the logarithm in base 10. But here, remember, we have discussed this trick before. This is the exponential of the logarithm of 10 to the y. Okay. And here now I can apply the properties of logarithms and bring the exponent y, bring it down. And now with this that I have written, I can already find the derivative. I just need to take the dx of both sides Okay, this is as before. Now, this is the derivative of the exponential is itself times the derivative of y logarithm of 10 equal 1. Now, the logarithm of 10 is just a constant, so we can pull it out. And what we get here is the exponential of y logarithm of 10 times the logarithm of 10 times dy dx equals 1. And now remember, here it's important always to remember why are we doing things, okay? So this exponential of y logarithm of 10, that's equal to x. Okay, so I might as well write it already. And then I realized that dy dx in this case is 1 divided by x logarithm of 10. And that's the answer to the question. Another important example is the function that is the natural logarithm of the absolute value of x. Okay, so this means this is the logarithm of x if x is positive, and the logarithm of minus x if x is negative, and 0 is not in the domain. So we have a function that looks like this. Okay, so it's symmetric respect to the y-axis, the vertical axis, and it cuts the x-axis at -1 and 1. Okay, so in this case we can just go ahead and do the derivative. Okay, in both sides the function is differentiable. There is a discontinuity at 0, but on either side of 0 there is no problem, so we can just go ahead and do it. So it's 1 over x on the right of 0, and then 1 over minus x, here I'm applying the chain rule, times the derivative of minus x, which is -1. So the first is if x is positive, the second one is if x is negative. But notice that it's the same either way. Okay, so here df dx is 1 over x for all x different from 0. And that's it. And one last example. This one is a little more obscure. So what about the function that is t to the power t? Okay, so far we have seen powers, right? That are t squared, t to the power 3, t to the power 4. Even I could take t to the power 4.5, whatever. And we have seen also exponentials that are like 2 to the t, 3 to the t, 4 to the t. These are exponentials. But t to the power t, this is different. Okay, so how do we handle this? We don't have a formula for this yet. Well, same trick. Take the exponential of the logarithm of t to the t and see what happens. Pull down the t using the properties of logarithms. And once we have it written like this, just go ahead and differentiate. Hopefully it will work. So apply the chain rule. This is the exponential of the function that was inside times the derivative of the function that was inside. And this is the exponential of t logarithm of t times 1 times logarithm of t plus t times 1 over t. Now remember, this exponential here equals the original function. So this is t to the power t times logarithm of t plus 1, because these two simplify. And this is the derivative, t to the power t times the 1 plus the logarithm of t. But of course, there's no point in learning this formula by heart, because it doesn't come up easily. Here, what is important is to learn the method. What we have done here, whenever we have some exponent that we don't like, we can always use the exponential of a logarithm to pull it down and then apply the chain rule.